So we'll be talking about how water can act as an acid or a base with itself. That's the first step in order to quantify exactly what it means to be a strong acid or a strong base, and calculate reaction equilibria for OH minus and H3O plus using the equilibrium constant there, which is in general, we talk about them being Kc, but for this particular reaction, we call it Kw, because special reaction gets a special label. We'll interconvert between OH minus and hydronium concentrations and pH as well. We use that reaction equilibrium to be able to quantify exactly how much H3O plus is being created. And then we'll calculate the pH of solution of strong acids and strong bases. So water can act as an acid and as a base with itself. It's called the AUTO-IONIZATION of water. So in this case, we have two water molecules, and one will give a proton over to the other to create hydronium and hydroxide. So the question is, how likely is this to occur? Well, H3O plus is a pretty strong acid, and OH minus is a pretty strong base. So you'd think that they would want to switch pass the proton back like a hot potato and go back to being two waters. And so what we see, if we look at the equilibrium constant here, now this is important, the equilibrium constant for this is H3O plus times OH minus. Why is water not there? Well, water is a pure substance on the other side. And so in its standard state, it is in its standard state there as a pure liquid. And so the concentration of H2O liquid does not come into play here. We're dealing with the AUTO-IONIZATION of just water itself. Okay. Right, as I said, it doesn't appear because it's essentially nearly pure. I mean, it's not pure to the extent you have H3O plus and OH minus, but it's essentially pure there. So for water, again, Kc is called, for this particular reaction, the AUTO-IONIZATION of water, the Kc is Kw. That's how it's usually tabulated and referred to. So we have H3O plus and OH minus in neutral water. And so it turns out that this equilibrium constant is 1.0 times 10 to the minus fourth. So this is, not really that much of hydronium hydroxide. The reaction equilibrium is really pushed towards combining them, handing the proton off from the hydronium to the hydroxide to create two water molecules. So therefore, let's assume that the solution is electrically neutral, so we have equal amounts of plus and minus ions. Therefore, we would have to have that the concentration of hydronium times the concentration of hydroxide, those are both equal to x. What's x? We don't know, but it's the same variable. Okay, so therefore Kw, which is equal to H3O plus times OH minus, that would be x times x squared equals 1.0 times 10 to the minus 14th. So therefore, x is going to be the square root of 1.0 times 10 to the minus 14. And taking square roots of things with exponents is easy. You just divide the exponent by 2. So this is 1.0 times 10 to the minus 7. So the concentration of both hydroxide and hydronium in pure water is going to be about 1.0 times 10 to the minus 7th molar. Okay. And so this is generally what we call a neutral solution of water. If we just have this amount of H3O plus and OH minus, their amounts are equal, then it is electrically neutral, and we call it it's neutral, neither acidic or basic. In order to keep track of these, nobody wants to keep writing exponents all the time. So we came up with a shorthand notation, pH, pH is common. You hear it everywhere. We know that a low pH is acidic and a high pH is basic. So the pH of solution is defined as the negative logarithm base 10 of the hydrogen ion, i.e. hydronium ion, in the concentration in moles per liter. So at 25, so we know at 25 degrees C, where Kw is 1.0 times 10 to the minus 14. So for acidic solutions, then the H3O plus concentration is above 10 to the minus 7, 1.0 times 10 to the minus 7 molar, which means the pH is less than 7. For basic solutions, the hydronium concentration is less than 1.0 times 10 to the minus 7th, as we just saw in the last section. And so the pH is greater than 7. And so for neutral solutions, it's the concentration of hydronium is right around 10 to the minus 7th. pH is near 7.0. I mean, you don't go around saying, oh, the pH is 6.95, therefore it's it's acidic. Well, it's close enough to being 7 to be neutral. So generally, if it's 7, if it's near neutral by, 1 log unit or so. So one interesting thing here is that, going back to this just for a second, this is a case where you do have to specify the units because, if you have a concentration of, hydronium, that's going to have units, say it's 0.1 molar, and you try to take the logarithm of that, that makes no sense. So for pH, you have to look at the concentration in molar, you chop off the molar and then take the logarithm here. So in this case, the pH is going to be minus log 10, 0.1 molar, but we get rid of the molar, is going to be minus log 10, 0.1, and that's going to be minus 1 or a plus 1. So that would be the pH if that was the concentration of hydronium. So yeah, you can't take a log of a molar. pH is defined in terms of the log of the concentration that is in moles per liter. One important thing to talk about for a second is to distinguish between acidity and acid strength. So an acid strength is how likely is the acid to give up its H+. Whereas acidity is how much H+ is there in the solution. So if you have a weaker acid, but you have more of it, the solution can actually be more acidic if there was sufficiently much of that weaker acid. Because remember, acids take what makes acids important is the amount of H+. And so if you're going to be judging by the amount of total H+, you could have a weaker acid that has stronger acidity because there's more of it, you get more H+. The acid strength is a measure of how likely an individual molecule of acid is to give up its H+. Okay. So yeah, so a very small amount of a very strong acid makes only a weakly acidic solution, whereas a lot of a weak acid can make a fairly acidic solution.